All right, everybody, I'm gonna start with the PC version before I can start doing the writing. Hopefully, the guy that can connect this to Zoom will get in here before I'm done with this. But there is a good portion I want to show you on most today anyways. We're looking at graphing sine and cosine today. So the graph of sine, if we just look at it, what we're doing is we're doing saying y equals sine x. So we're gonna plug in, use x as our angle. So we'll use angles like the ones we know, like 0, pi over 6, pi over 4, pi over 3, pi over 2. We can generate points along this curve, and I'll make you a list when we got that, and we can do the camera a little bit better. But we'll see that it makes a wave. And the wave repeats. And we can see if the, like right here, that value is, where this is 0. I think another way of making it show 0 is just saying y equals 0 and showing where they intersect. There we go. So it goes up and it comes back, it goes down underneath, and it goes back to 0 every 2 pi. These are called periodic functions. A periodic function repeats after every period. In this case, the period is 2 pi. You'll notice it'll go up again, it comes back down again. And the next time it's back to 0, doing the up and down, we're back at 4 pi. So every 2 pi, sine repeats the graph of it. We can have multipliers in front of it. And let's take a look at doing what something like 4 sine x does. Having a 4 in front of it takes the height from having a height of 1 right here up to 4. So it's just rescaling it vertically. So the number in front rescales vertically. Same thing if we cut it in 4, we're going to have a really short graph. So instead of going up to 1, it goes down to 1/4. That's what the number in front does. That's outside the sine function. The same thing is going to hold true with cosine. But it's gonna, the graph is different, but that number in front will affect, it's called the amplitude. And I'll be writing all this down in a second. Hopefully Ray comes in here before then, but if not, people online will miss out. So this number in front is called amplitude. We usually call it, give it the letter A for a generic letter. If we look at something in front of x inside the trig function, I'm going to show you 2x first. Now it's a little hard to like follow, but look at like the black one is our original and it repeats every 2 pi. This one is repeating every pi. And if I do the one that has 1/2, it goes up, down, up, or it goes up, back to 0, down, back to 0 every 4 pi. So having a number in front, we usually give this letter B. As you'll see down here, B. It takes the period and you divide the period of 2 pi by that B and it gives you the new period. It makes the period different. How often it repeats. So we can put it all kind of together here. And so as B changes, as B gets larger, the graph scrunches down, starts repeating faster. And when B goes lower than 1, B equals 0. B equals 0 is just making this sign a 0, and so we don't have really a graph anymore. But something small makes it not repeat very often at all. And likewise, we can affect the scaling, the vertical scaling, by increasing A. A gets small, does that. A gets lower, it gets flat. What do you think happens when A is negative?
So
It flips over. So if we do A equals -1. Now, rather than going up first, it goes down first. But it is still repeating over. Oh, now it's not. There it goes. It's still repeating over a period of 2 pi. So if you remember from algebra, you used to be able to write the functions as f of x with x minus h and a k. I've got that listed here. What does that do here? I'm gonna turn off this. I like the y equals 0, but I'm gonna change the color. So as we change h here, if I make h positive, the graph moves to the right. And if you do it the right amount, it will get to exactly where it was before. This is kind of what happened with algebra. If you had the x minus h inside of a function, having a positive h moved it right, having a negative h moved it left. So if we make h negative, I'll put this back to a equals 1. We have h go negative. Let's go back to 0. As h goes negative, the graph is shifting to the left. Does anyone remember what having a number at the end does to the graph? From algebra.
Moves it up and down.
It moves it up and down. It's exactly what it does. So k, positive k is going to move the graph up. Negative k is going to move the graph down. But notice the shape of the graph doesn't change unless A or B changes. A will change the height. B changes how often it repeats. But H and K just change where it centers at. Let's go back to 0, 0 there. I'm gonna turn that one off. We can leave that one off or on. That's sine. Let's take a look at what cosine looks like. Cosine is the one in orange. Looks like the same graph, doesn't it? It is. It's effectively the exact same graph. It's just shifted over exactly pi over 2. Where when cosine is 0, when sine is 0. Let's. Easy way to look at it. Cosine is 0 at. Sorry, cosine is 1 at 0. But sine is 1 at pi over 2. So it just shifts everything by pi over 2. The entire graph is shifted by pi over 2. But you'll see when we look at how cosine works. Same properties go on. If A gets bigger, number in front, the amplitude gets bigger. As B gets bigger, it repeats more often. And if B gets smaller, it repeats less often. I don't know that B going negative does anything here actually. That's B equals 1. And B equals -1 here. It's like that. It's a property of cosine. Cosine is an even function. So cosine doesn't change when B equals -1. Watch what happens with sine. There's the original sine. There's the sine with B equals -1. So cosine didn't change by having that negative number in there, but sine does. Sine is an odd function. In fact, what it's doing is it's flipping everything over the x-axis. It looks like it's flipping it over y, but it's really flipping it over. Looks like it's flipping it over x, but it's really flipping it over y. And we'll look at the other ones more often. Then I gotta go back to the document camera because so much we can play with this without writing down some stuff, sorry folks online. Uh. We'll do what we can when we can. I'll leave that screen up for you so you can enjoy it. At least the graph thing. I'm gonna come back to do a pulling problem from 6.2 a little bit later. So graphs of sines, this is, we're doing 6.3 and 6.4. Six point three is the basic graphs of sine. And cosine. And 6.4 does all the shifting and translations is what they're called. So. First thing is periodic functions. I mentioned this earlier. Periodic functions have graphs that repeat. So f of x equals f of x plus np, where p is the period. And n is some whole or integer multiplier. So that means I could graph y equals sine x. Let me say this real quick, period of sine and cosine are 2 pi. So y equals sine x has the same graph of sine x plus 2 pi. Oops. Has the same graph as sine of x plus 4 pi. Or a general form as we say 2 pi n. Rather than putting the p after the n, the pi kind of, we like tend to put things that are variable at the end. So if we make like a chart, a table for the values. X and Y. We kind of want to stick to the values that give us nice pretty numbers. Don't throw in 1 degree, in fact, I'm going to use radians rather than degrees. 0, pi over 6. Pi over 4. Pi over 3. Pi over 2. And then rather than going every, like the entire circle going all the way around, let's just do multiples of pi over 2. So it'll be pi and 3 pi over 2, 2 pi. Some of you have memorized these already, which is good. What is sine of 0? 0. What about pi over 6?
15,
What?
30,
That's 30 degrees, what's the sine value though?
Half.
1/2. Pi over 4? Square root of 2 over 2. Pi over 3. Square root of 3 over 2. And pi over 2 was effectively square root of 4 over 2, which is 1. Now this would go back down if we kept going, doing the quadrant 2, but when we got down to pi, sine of pi was 0. Sine of 3 pi over 2 was -1. 2 pi was 0. And effectively, if you did like 2 pi plus pi over 6, you're back up to 1/2. You'll start seeing that this repeats. Okay, so when we're doing graphs, we like to talk about the domain and the range. Domain was all the possible inputs of x. And we saw when we zoomed out, that graph kept repeating as we went left or right. The domain is negative infinity to infinity. The range, the smallest value we have here is -1. And the largest value we have here is 1. So the range is -1 to 1. So this is just the base graph. We saw that changes when we do amplitudes and stuff like that. But the base graph just does this, and it's important to know how the base graph works. Sine of x is continuous over its entire domain. You may not be impressed with the importance of continuousness or continuity yet, but when you get to calculus, it's important. And it has a lot of x-intercepts. When we looked at the graph. The x-intercepts. Which is where y = 0. We can see it's at 0, pi, 2 pi. It's at every multiple of pi. Oh, the man is here. Even stronger. Let me change the share here. That way.
this can't be cheaper when you again.
No, I'm it's like a bad luck charm here.
I already talked to media services guys and then I think Friday be out here and take a look and see if they can't see. What?
I'm one of the few teachers that likes to do the Zoom and report and stuff, so. I'm the one that gets to find all the glitches.
What's the password?
It's gonna say multiple of pi. Mainly, we're still on the first page for people at home. And we haven't really said anything that I didn't say out loud. Now, full range of scores on the test. We had a 0 and we had a perfect score with the extra credit. I wanna say a lot more people passed than didn't. Which is what I wanted. I didn't actually look to see, quantify that yet. But I know going through it, I know I was typing in. Over 140 was 140 is 70%. So if you had over 140, you got above C. And I wanna say most people were above 140. Every once in a while, someone was below. It's probably not studying enough. It's a good wake up call. You do have time to turn your ship around and get back on course and still pass the class.
The scores in the notebook are including bonus points?
Nope.
No?
But they're extra credit from the test, but not from doing the homework,
Uh,
because there was options on the test for extra credit.
We can get a copy of what happened.
Yeah, I'll give you your test back. You would have had it today, your teacher was a better teacher. But he left that shit at home. It's doing it, I see it, excellent.
Okay, so we kind of narrowed it down to another piece of equipment that they're going to take a look at. Are you in here like every
I'm
Wednesday?
on Mondays and Wednesdays and then
Okay.
121 on Tuesdays and Thursdays.
Okay, so so next Monday, he'll be back in here.
Yeah,
So, yeah, if it works or if it doesn't work on Monday, yeah, we'll be able to. Cause there's two pieces of equipment in there that work with that. So
narrowing down
hopefully
which one it is.
narrowing down which one it was, so, yeah.
Thank you so much, Rick.
Oh, you're welcome.
Told you guys it's quick.
When you kind of know what you're looking for. When you're
Well,
not.
I mean, even responding.
Oh, well, yeah, you got lucky. I was looking at my email.
I've gotten it lucky every time then. Tend to be pretty quick. Thank you again. Have a good one. You too.
Sorry, well, it's not.
Alright. So where was I? At every multiple of pi. I got so excited, I stopped writing right away. So like, the way we use n up above, we could say they're at n pi. Where n is a whole number or an integer. Y equals sine x is an odd function. I was mentioning this a little bit ago. Which means when you have y equals sine of negative x. It equals negative sine of x. We showed that on the graph when we did a equals negative or b equals -1. It was sine at second. And if you remember about symmetries, this is the weird symmetry. Or sine is symmetrical with respect to the origin.
not a case with cosine.
It's not the case with cosine. Cosine has a much friendlier symmetry. Symmetry with respect to the origin is really hard to fucking picture. Symmetry over y and symmetry over x are easy, they look like mirror images. This is like symmetry in a weird way. And we'll graph it out in a second, well, we'll graph it out since people are done writing this. Why does this look so weird? There we go, the thing was tipped up at a weird angle. Anyone need that longer? Okay, let's take a look at graphing it. Graphing sin x. Pro tip. Just do multiples of pi over 2. We know the graph of sine is not very tall, it only goes up to 1 and -1. And since I'm gonna be doing pi over 2. I'm not gonna put in 1, 2, 3, 4 along the horizontal axis, I'm gonna do pi over 2. So pi over 2. Pi. 3 pi over 2. 2 pi. And we'll go the other way. A little bit, negative pi over 2, negative pi. Negative 3 pi over 2. If it helps you remember, when you're picturing the unit circle, sine is the y value on the unit circle. So at 0 degrees or 0 radians, sine is 0 here. And we were just saying this, it's every multiple of pi at a 0. You can fill those in relatively quickly. What is sine of pi over 2? What? Sine of 3 pi over 2 was -1. Do not do this. Make it curvy. And it's gonna keep going. And once you graph 0 to 2 pi. You can work backwards just following the curve the other direction. This should go down. Goes like that. Back up. Up to 1. So the symmetry about the origin, I'm gonna do with a blue line here. Actually, I'm gonna do it with a dashed line. If I go this far in this direction, a distance d. I can go that far the exact opposite direction, a distance d, and I'll hit the graph. That's what symmetry about the origin meant. And assuming I drew the graph well, those should be the same length. They're equal in opposite direction, get you the same point on the graph if you start the origin. Any questions? Cosine. Is the same as sine x. Shifted left pi over 2. So sine of pi over 2 is 1. So we go left pi over 2, we're at 0, cosine of 0 is 1. I'll make a quick table of the cosine values. Again, we'll do the basic ones in that first quadrant. 0, pi over 6, pi over 4, pi over 3, pi over 2. And then we'll do every increment of pi over 2. Thank you, Owen, for the email. Appreciate that. You let me know yesterday that I had put all the test scores in the homework column. So I went in there and like changed it as quick as I could, so it didn't look like a scrub to everybody. But then I told the class right now, so it's fine. So if you went to look right away, I would have said your test was a 0. What the fuck? Who saw it before I fixed it? Yeah, a lot of people. Alright. Cosine of 0 was 1. Pi over 6 was the root 3 over 2. It was the same thing as sine, but in the opposite order. And then pi was -1. 3 pi over 2 was 0. And 2 pi was back to +1. So, domain and range again. What color did I use last time? I used green for domain and range, we did that here. Domain and range is the same as sine. We had negative infinity to infinity and -1 to 1. Cosine x is also continuous on its domain. So next thing we talked about were x-intercepts. It looks like they occur at pi over 2 plus every multiple of pi, so we could say plus n pi. Another way of writing that is saying 2n plus 1 times pi over 2. These two things are the same. If you get a common denominator and factor out the pi over 2, that's what you get. Y equals cosine x is an even function. So like the odd function, we stuck in negative x and it made the function negative. When we stick in a negative x here. It's the same thing as not having a negative in at all. And this creates a symmetry about y. Cosine x is symmetrical across the y-axis. Across the y-axis. Ready to graph it? You're gonna find we're gonna do something similar. We're gonna do the multiples of pi over 2. It makes kind of graphing it not too bad. Let's go every pi over 2. -1. The easiest way to do this is you know the values of cosine at these functions. Cosine of 0 is what? 1, right?
1,
Cosine of pi over 2 is 0.
0,
Cosine of pi,
-1,
and you'll see we're going up and down, up and down. And we even said that every pi over 2 and then add pi, we were at 0. Those are our intercepts. It should follow this wave-like motion. The base graph of cosine is this. And then it starts to repeat. In fact, I'll leave the red part as the base and show the repetitions in green.
Zero.
0 and 2 pi, yeah. Both sine of x and cosine of x. The base period is 0 to 2 pi. So let's introduce something different. Let's take a look at y equals a sine of bx. Or the equivalent holds true for y equals a cosine of bx. What this does to the graph is the a changes the range. From -1 to 1 to -a to a. B changes the period. From 2 pi to 2 pi over b. So this green red line up here was y equals cosine x. I'll make a blue line. We're gonna do y equals 1/2 cosine x. This is just changing the a, so a equals 1/2 here. The way you use this is the zeros stay the same, because anything times 0 is 0. But everywhere you had a 1, you're gonna go a. So instead of going up to 1, we're gonna go up to 1/2. And instead of going down to -1, we're gonna go down to -1/2. So our points will look like this. It flattens it, it smooshes it. Zeros are still the same, it just makes it. Actually, both kind of neat, if you're on Desmos and you have like a whole bunch of them listed. Like cosine x, cosine 2x, cosine 3x, cosine 4x. Or the a on it, sorry. Cosine x, 2 cosine x, 3 cosine x, it looks like a arc, really cool arc. Let's take a look at y equals sine pi over 2x. So what we did with sine before b. Before we were taking b, we started with 0 to 2 pi. And broke it up into 4 regions. Zero to pi, we went to pi, we went to pi over 2, we went to 3 pi over 2. And we did our graph. So we broke it up into 4 regions. Region 1, 2, 3, 4, like our quadrants. When we have b, we're gonna break up 0 to 2 pi over b. into 4 regions. And follow the same pattern. Base pattern. Laying down law. Fuck that motherfucker, get out, not even get out, just you're dead. I'm cool with that. So like. What do we got here? B is pi over 2, so our period. Is gonna be 2 pi divided by pi over 2. Which is a little awkward, but remember, we can multiply by the reciprocal. Thing on bottom. 2 over pi times 2 over pi. That cancels, that cancels. And I've got 4 pi over pi, which is 4. So, rather than our axis or graph being along every pi over 2, we're going 0 to 4 and we'll break this up into 4 regions. Easiest way is to cut it in half once and then cut those in half again. I make this a little taller. This is my x-axis, my y-axis. Going up a height of 1. Sine was 0, 1, 0, -1, 0. Take a 10-minute break. Alright, so we talked about. At least on the camera, what happens when we shift the graphs. If I have sine of x plus 2. The entire sine graph, in fact, the way I would do it. Is plot the pi over 2, every pi over 2. I would plot the, or just do the points for the base graph. Not actually draw it. So we got our zeros at our pi's for sine. And then we got 1 and -1. And then move it up 2. Just take all these points and move them up 2. And graph there. And obviously it goes to the left. And keeps going. And if I'm gonna shift it on the inside. Let's say I have x. Plus pi over 4. You're gonna move it the opposite direction of this. So it's positive pi over 4, positive generally to the right, so here we would move left pi over 4. Since each of these little points is pi over 2. The pi over 4 is like halfway. And what happens is we shift all of our points left pi over 4. So this is going left, 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 left. And we do our wave now. So that is that line. And that is that line. Davis was talking about it over while I had that recording off. Light and sound all travel in these sines and cosine waves, they travel in waves. Where the wavelength is really like redefining the period. If you take physics, you can learn about it, but literally like start two of our senses that we rely on the most, sight and sound. You can break down mathematically into this, they're all waves. And this is a wave. So, in general, let's say we've got y equals a times sine. I'm gonna factor out the b and write it like that. Or we can do y equals, same thing with cosine. The strategy is gonna be the same. There's two strategies. One is, I think, much quicker, but it requires you to know the 5 basic points. The 0, the pi over 2, the pi, the 3 pi over 2, and the pi. 2 pi. On both of them, well. Option 1. I'll give you both paths. Find the period. P equals 2 pi over phi. And break the period. Or the region. 0 to 2 pi over b up into 4. Into 4 parts. Like we did earlier. So that's kind of like part 1 or A, all of A. B. Plot your zeros. Your intercepts. And your 1 and -1, but multiplied by A. Once you got this is really easy at this point. If you got the B factored out, and it's important you have the B factored out, otherwise you're gonna move it the wrong way. Or move it the wrong amount, at this point. Move those points. Right H. Up K. Or if H is negative, left. And K is negative, down. Thank you. This movement of H, this is called the phase shift. If you hear the phrase phase shift, it's how much you're shifting left or right. This is a pretty easy pattern to do, especially if you use it exclusively, you get really fucking quick at it. The next way, option 2 is slow every fucking time, but it doesn't require you to use your brain very much, so some people like that. I recommend option 1. Option 2 is very much calculator based. So, everyone ready to look at option 2? So for option 2. Find the period. By solving. 0 is less than B times X minus H. Which is less than 2 pi. So like, let's say this one might be easier to have for an example. Let's say we had. 0 is less than or equal to. 2 times X minus pi over 4. I would divide by 2 and I would get 0 is less than or equal to X minus pi over 4. Which is less than or equal to pi. And then I would add pi over 4 to all regions. Pi plus pi over 4 is. Same thing as 4 pi over 4 plus pi over 4, 5 pi over 4. This is doing your left-right shift right away. You've compensated for your left-right shift right away. But it tends to make dividing this into 4 regions fucking harder. We still need to divide it into 4 regions. So that's part 1. Did I use option K? I said option 1 earlier and then I said option B here. Let's call that 2 and I'll use A. B, break that up into 4 regions. The way I would do this, continuing the example. Take the larger one and subtract the lower one to find out how wide it is. So it's pi wide. So to break it up into 4. I gotta do this thing divided by 4. Increments. So what I would have pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. And yes, some of those do reduce quite easily, but if I show it in reduced form, you're not gonna see how the pattern works. You now have your x values for where your graph is, now you just need to find the y values. Find the y values. By plugging. Those 5 points. 5 x values. Into your function. And evaluating. I'll do a quick example on this one using the things we had before. Say our function was y equals 3 cosine. 2 times x minus pi over 4. That way we're using the same shit plus 1. When I do x equals pi over 4. I get y equals 3 cosine. 2 times pi over 4 minus pi over 4. Plus 1. This is 3 times cosine is 0. Plus 1 or 4. I will have a point at pi over 4, comma 4. And do this for all 5 points. And then you don't have to do any shifting, you have your h's, your k, every hk, everything is compensated for, a is compensated for. But the k can get ugly and. I think it's easier to do the other one, but. To each their own. There is advantages to this one. The advantages to option 2. Is. A negative amplitude is already accounted for. And I should have mentioned in option 1 and I didn't. Go back, add to option 1. I will, I'll go back to add to option 1 if I got room. Option 1. You have to flip the graph. If A is negative. And some people don't remember to do it. It's easy to forget the negative part. Let me go up here, it's here. If A is less than 0, flip the graph. That's what I changed on the previous page. You will be asked to graph by hand some functions on the test. So we're gonna go over doing some examples here real quick. Okay. See some pins still going, so I will wait. Okay, so let's do y equals. Four minus two sine of 3x minus pi. So first thing I'm gonna do is I'm gonna rewrite it to look like the form that we had. I'm gonna move the 4 to the end. And in here, I'm gonna factor out the 3. And make this x minus pi over 3. I'll do option 1 on this one first. So our base period is 0 to 2 pi. But we need to do 2 pi over b. B here is 3, so 2 pi over 3. You will often find that finding the 4 points or the 4 regions is a little bit easier. A little easier if I multiply by 4 over 4. In general, in this problem I can get away with 2 over 2, but I'm gonna do 4 over 4. This gives me 8 pi over 12. So I'm just gonna go out, I'm gonna pick out. Set my own axis here, this is gonna be 8 pi over 12. And I will cut that in half. Dividing in the half is 4 pi over 12. And cutting this in half would be 2 pi over 12. And halfway between this looks like it's going 2, 4, blank 8. This is 6 pi over 12. These obviously reduce to simpler values, but it does make it easier to see what you're applying for. Normal values of sine go like this. I will have those same values, but I'm gonna take this and multiply this by a, which is -2. 1 times -2 is -2. And this one was -1. -1 times -2 is +2. So now my graph is looking like this. And I haven't done my phase shifts yet. Now I need to move it right pi over 3 and up 4. Again, the easiest way to do this right thing is multiply by 4 over 4. So I'm moving everything 4 pi over 12 to the right. Which means I need to add a couple more things here. We'll go up to 12 pi over 12. And I didn't give myself room to go up 4, did I? So I'm gonna redraw this right down here. Same values. So 2 pi over 12. 4 pi over 12. 6 pi over 12. 8 pi over 12, and that went over to 12 pi over 12. And it looks like I need to be able to go up to 6 now. This was at -2 and 2. I'm actually gonna show it here on this graph real quick. The points we had. We had 0, -2, 0, 2, and 1. And now I'll do my movement. I'm gonna go right 4 pi over 2 and up 4. So this point goes right 4 pi over 2 and up 4. That's like point A is now over there. This one goes 4 pi over 2 to the right and up 4. Oddly enough, B moves to where that is now. This one's right 4 pi over 2. It should be on the same height as this. It's at the same height as A. So that one's there, and we actually know 8 pi over 12 is at the same height as A there. So I can move those. That went there. That went there. That's going there. there. Finally, the 6 pi/12 goes right, 4 pi/12. And up 4 is right about here. It take a little bit of work. I know. That make sense? Not necessarily, that question is, was that easy? But does it make sense? Find our base period, break it up into 4 points. Plot the points with the amplitude. And then shift them HK. We'll do another one using the other method. Ready for another? Okay, let's try. Y equals 3/2 cosine of 2x minus pi. And I'm gonna do this doing option 2. If you do this doing option 2, you do not need to rewrite the equation, we just need to take this middle value here. And plug this in between 0 is less than that. Is less than 2 pi. And solve. You know what, I wanna make this 3x minus pi. Simply because 2x is easier to work with and it's gonna automatically make this method look easier. Let's use 3x minus pi there. So I add pi to both or all sides. I get 0 is less than or equal to 3x, which is less than or equal to 3 pi. And they divide by 3.
I'm sorry, is 0 plus pi not pi?
It is pi. Thank you. I'm like, that looks fucking funny. That looks way too easy. Now it's not so easy. We divide by 3. And we have pi over 3 is less than or equal to x, which is less than or equal to. I'm gonna leave that listed as 3 pi over 3. Because we do need to break this up into 4 regions. And keeping the same numerator or same denominator makes this a lot easier. I'm gonna multiply both of these by 4 over 4 like we did last time. This is 4 pi over 12 less than or equal to 12 pi over 12. Oh, let's add in a -1 up here at the end of that. Well, we might as well have something, do everything on it. So what we have here is now we are not gonna have to move along X anymore. If I say that's 2 pi over 12. I'm spacing it like this. That's 6 pi over 12. 8 pi over 12. 10 pi over 12. And 12 pi over 12. And does that actually give us 4 regions? That actually gave us 4 regions. I got lucky here. So we're breaking up into that region to this region. Again, if you want to see how far you need to move, you can take these and subtract them. 12 pi over 12 minus 4 pi over 12 is 8 pi over 12. That's the width. So if I want 4 increments, I multiply that by 1/4. I get 2 pi over 12 as our increments. And that's what I have listed here, every 2 pi over 12. At this point, you're plugging these into that equation up there. Let's do the first one here, y equals 3/2 cosine of 3 times 4 pi over 12. Minus pi, minus 1. Trying to find the y value for it. That is 12 pi over 12, which is pi. Minus pi is 0. This is 3/2 cosine 0 minus 1. Which is 3/2 minus 1, which is 1/2. So the first point would be right here. Then we gotta do the next one, plug in 6 pi over 12. This is 3/2 cosine of. That's 18 pi minus 12 pi is pi over 2. Minus 1. Which is just. -1, right? Cosine of pi over 2 is 0, so that's just -1. Looks so funny. What did I fuck up here? This feels wrong. Oh well, I'm gonna do the rest of the points, we'll find out. Y equals 3/2 cosine. I'm sticking in 8 pi over 12 now. This is 3/2 cosine of 24 pi over 12, which is 2 pi minus pi. This is 3/2 cosine of pi. -1, this is. Negative. That's -1, so -5/2. No, this is right, I just fucked up and wrote where I need to graph. And once we have these, we should be able to get the other ones. Just by moving over and doing the same amounts, so we know it goes back up on cosine. I don't know, they both have their cons, this one, you're only doing the graph once, you're not shifting it or anything. But like the work in getting the points is a little bit more of a bitch. The other one, getting the points was easier. Especially when you start with like something like, sometimes this is ugly, like pi/6 or some shit, weird shit. Does that all make sense? Okay. I will show you secant and cosecant later on, or on. Was it Wednesday, so Monday? I do wanna pull something that we did in 6.2. There was one more topic. That I wanted to, not topic, but example. Gotta find the damn thing. There we go. Does anyone need that? Some people are receiving. Yeah, please. I'll start writing the question for those of you that are. Ready for the question. Belt runs a pulley. Radius 5 inches. At 120 revolutions per minute. A is gonna be find the angular speed. In radians per second. And B will be find the linear speed in inches per second. So like we got like a. There's a pulley. And it's got a radius of 5 inches. And this motherfucker is rotating quickly. Boom, 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 boom. As a reminder, the equations we had. We had V equals R omega. We had omega equals theta over T.
We're gonna use V equals, velocity equals radius times omega.
That will be for our linear speed. Our angular speed is that one. So, doing our angular speed. Omega equals theta over T. We have 120 revolutions. Per 1 minute. And I wanna end up over here with radians per second. So what I gotta do is start doing stuff that cancels this out. First thing I can cancel out is I know there is 1 minute per 60 seconds. That will cancel out minutes, and now I've got revolutions per second. We're getting closer. A revolution is one full rotation. How many radians is one full rotation? We go full circle, how much is the angle?
2 pi over
360, but in radians, it's 2 pi.
3.
One revolution is 2 pi radians. If you needed to shift to 360 degrees first, that's fine. But at that point, you're gonna have to do pi over 180 degrees to get to radians. So that's another option for that step right there. But now revolutions cancel out. And I'm left with radians per second. So I've got 120 over 60 is 2. 2 times 2 pi is 4 pi radians per second. So it's rotating twice per second. Full circle, 2 full circles per second. And find the linear speed. We have omega and we have r, so we can find the linear speed. E equals r omega is 5 inches times 4 pi radians per second, which equals 20 pi inches per second. And that's probably not all that useful for most people, since we're talking about an actual length. 20 times pi is 62 point, you round to 3 decimal places, or 2 decimal places. 62.83 inches per second. So I know there's problems like that in 6.2, and we didn't do a pulley problem. We didn't have something with rotations. I'm sure there's a problem in there that describes a CD or a DVD or some shit like that. A pulley rotating does the same thing. That's all I've got for you folks. Have a good weekend. As a reminder, I'm in the Mid Center on Saturdays, 8 to 2. Stop by. You got questions?
Have a good one. Take care.